Ask an AI to build Zepto's inventory system and it will give you a database query. Clean code, correct logic, working tests. What it will not give you is the decision to put Redis in front of that database. That one decision is the difference between Zepto handling 10,000 requests per second and going down at 9 p.m. on a Friday. In the next 8 minutes, you will learn caching and why this single architectural choice is what separates a developer who writes code from an engineer who builds systems. 5 things you will own after this video: the database bottleneck, the cache aside pattern, time to live invalidation, the cache stampede failure mode, and the survival skill, the exact judgment call AI misses when designing caches. If you watch this video to the end, you will be able to answer a caching architecture interview question better than 90% of candidates who have been building software for years. Let us build it. Here is the AI default. A user opens Zepto and looks at milk. The app asks the gateway for the inventory count. The gateway routes the request to the inventory service. The inventory service queries PostgreSQL directly. It works until Friday night. Suddenly, 10,000 users are looking at milk simultaneously. 10,000 database queries per second. PostgreSQL CPU hits 100%. The database locks up. The app crashes. Why? Because databases write to disk. Disks are slow. You cannot serve read-heavy traffic directly from a database. Here is the correct architecture. Cache aside. Before the inventory service touches the database, it asks Redis, do you have the inventory count for milk? Redis is in memory. It answers in under 1 millisecond. If Redis says no, this is a cache miss. The service falls back and queries PostgreSQL for the true count. The service gets the count from PostgreSQL, but before it returns the data to the user, it writes that count into Redis. Now, the next 10,000 users who look at milk never touch PostgreSQL. The inventory service checks Redis, gets a cache hit and returns it instantly. 10,000 database queries become 0 database queries. The system survives. But inventory changes, someone buys the milk. How does Redis know the data is old? When the inventory service writes the count to Redis, it adds a time to live or TTL. It tells Redis hold this data but automatically delete it in exactly 60 seconds. 60 seconds pass, Redis automatically deletes the key. The next user who looks at milk triggers a cache miss. Redis returns null. The cache is empty. The service goes to PostgreSQL, gets the absolute latest inventory count and writes it back to Redis with a new 60-second timer. The data is never more than 60 seconds out of sync, but TTL introduces a critical failure mode. The exact failure mode AI ignores. Here is the trap. Milk is extremely popular. 10,000 users are looking at it every second. The 60-second TTL expires. Redis deletes the key. In that exact millisecond, 10,000 requests hit the inventory service. All 10,000 threads check Redis simultaneously. They all get a cache miss. Because they missed the cache, all 10,000 threads pivot and query PostgreSQL simultaneously to rebuild the cache. The database instantly crashes. This is a cache stampede. How do you fix it? A distributed log. When 10,000 threads miss the cache, only the first thread is granted the log to query the database. The other 9,999 threads are forced to wait 50 milliseconds and check Redis again. The database survives. If this kind of decision making is what you want to make confidently, subscribe now. Every Tuesday, one judgment call free. Let us look at the trade-offs. We used cache aside. The application manages the cache. Another pattern is write through, where the application writes to the cache and the cache synchronously writes to the database. Cache aside is perfect for Zepto because it is read heavy. Users look at items far more often than they buy them. Write through guarantees perfect consistency but slows down every single write operation. I will write cache aside code without locks. The engineer adds the distributed lock to prevent the stampede. Full recap: Hop 1, customer requests inventory. Hop 2, the inventory service checks Redis first. Hop 3, if there is a miss, One thread gets a distributed lock and queries PostgreSQL. Hop 4. The thread writes the data back to Redis with the 60-second TTL. Hop 5. The next 10 million requests are served instantly from memory. Zero database load. You now own the architecture. Let me close with the one sentence that makes this judgment stick. The Redis decision is not a line of code. It is a judgment call. Judgment is what AI cannot generate. Before this video, if someone asked you to scale a system, the answer was just use Redis. After this video, the answer is we use a cache aside pattern to shield the database, apply a 60-second TTL for data freshness, and use a distributed lock to prevent a cache stampede on expiration. That distinction is your job security. Next Tuesday, event driven design. What happens when a payment succeeds, but the inventory update fails? If you use standard API calls, you lose the order. You must use Kafka. See you Tuesday. Subscribe to ByteLearn for the complete One Engineer System series. One survival skill every Tuesday. Hit the bell question. Have you ever taken down a database because of a missing cache? Confess in the comments.